Good morning, good afternoon, good evening, everybody. It's my pleasure to introduce Dr. Kota Harinarayana, I have known for the last 20 years, one of the most delightful and humble person I've met in my life for all what he has accomplished. And today his lecture will be Tejas, Fighter Jet Development, Pleasures and Pain of Engineering of a Complex System. He is chair of the board of IIT BHU and chief architect of Tejas. And I won't go any further with the introduction, and I will hand the mic to him to start the lecture. Thank you very much for joining us for this lecture, and the mic is all yours.
So, thank you for inviting me. Uh, I want to present it in the following fashion. I'll show the next slide. I want, because not everyone is from aeronautical industry. So I thought some typical characteristics of the aeronautical industry I would like to bring forward. Then I will quickly show what Tejas has developed, what we have achieved. Then some analysis of what has been achieved, what are the issues, what are the problems. These are the three parts what I would like to present across. So first, let me go to the characteristics of aeronautical industry. What I'm presenting now will be a presentation given some time back by our Brazilian industry, but it's a typical characteristic. What happens? It is for a civil aircraft, but for a military aircraft, sometimes it may take a little longer because in a military aircraft there are hundreds of weapons and all have to be integrated till a number. But this is the typical characteristic that happened there. So what is the characteristic of aeronautical industry? You need highly qualified people. Manpower is very, very important. Then multidisciplinary technologies, many. So in an aircraft like light combat aircraft, we had at least 40 different discipline people working together. And investments are in billions of dollars, a huge investment. And that is what prevents many countries to venture into it. And fourth is a long maturation time, very long. Typical time for a ab initio design from technology development will be not less than 2 decades. And global based clients, though you develop it, but the clients, suppliers, everybody from there, and not many organizations who are capable of doing this. There are very few. And fingertips, even today, if you see, there are not many who are able to develop first aeronautical products which make sense. This is the characteristic. Now, you are in multi-billion business. Innovation is essential for competitiveness and also survival. Okay, if you that is a continuously you have to continue to involve, and so technology development becomes a vital element of any aircraft development. So you are in the circle where you develop technology, development of technology, innovation, investment. They go in circles. And here, a global and innovation supply chain, qualified and passionate people. This is what is very important. The passion is very important. I'll talk about it. And collaborate for technical development. And support from government is very essential. Whether it is USA or Europe or India or China or Russia, the support from government, whether it is civil program or military program, of course, military program government support is there fully, but even civil program or Canada, the government support is vital. In fact, without government support, none of these industries would be able to come out with front-ranking aircraft. This is very important there. And this is familiar to all of you. What I want to show is typical civil aircraft takes 20 years, a little more in a military aircraft. So 20 years average is what it is taking from TRL-1 to TRL-9, right from basic technology, research, development, technology, demonstrate, and subsystem development, and system test and operation. And quite often, from technology development to system development, that intermediate stage, that is where the investments are high, and that is where quite a few of the programs, they didn't get support and they failed. So this is what happens quite often. So as I've shown here, basic technology, $100,000, then you come to 1 million, then 10 million, then 100 million, then billions. That is the kind of you need at least 10 million to demonstrate in a meaningful way. And then only you can go to a subsystem and system, which goes into 2 billion, 3 billion. That is the kind of a thing that what happens. So this is the characteristic of time, technology development, and money. I'm showing this slide to show that when you come to that TRL level 6, where investments are very high, and quite a few programs, they died. Okay, so we have to overcome this kind of a death scenario. Hundreds of programs have died. So we had a big challenge here, this kind of a thing. And as I go by, I'll be able to say how we got into problem and how we got out of the problem. Today, of course, we're in a much better place. I want to give one example of Eurofighter Typhoon. This fighter was developed jointly between what you call UK, Germany, Italy, and Spain, 4 countries together. And it took them something like 25 years, where first flight on a Jaguar fly-by-wire system, which is the new technology, they did from 1977. Then they took an experimental aircraft program, and that went on from 83 to 91, full-fledged development program. That they went up to 2008, continuing further FOC1, FOC2, and all that kind of a thing. So you could clearly see with all the giants in the field, all the 4 countries have got a very high expertise, technology base, and legacy of developing aircraft. So, but that is the kind of time it takes for development. I'm telling this because in India, because of lack of experience and all, there are a lot of criticism about the time taken for LCA program. And this is what it takes. But now people realize that was the criticism earlier, but not so. So if you see here, we got at least seed money to get on with the technology development in initial studies. But it was only in 1993 to develop the technology on a new aircraft. Again, technology is not operational aircraft. We got the clearance. And it is only in November 2001, after the aircraft flew, the technology demonstrator flew, we got the clearance. And then it took us almost another 12 years to make the IOC. FOC and all were going on. We continue to do that, but the IOC is the most important. So that is the kind of time frame which takes from 1993 to this, almost 25, 26 years, from what you call technology demonstrator program to the final clearance. So this is what it is. Now let me just 1 or 2 slides on. Among the front rank weapon system, aircraft has been the biggest impact on military as an outcome of the war. You are now seeing the Ukraine war from manned to unmanned impact. You just can't manage a war unless you have the what you call superiority in air power. This is what is required. And we're seeing in all wars what happened. Where there is no superiority, there is no winning. So, of course, the biggest what you call impact of a fighter came in Second World War. And the post-Second War period, the role of aircraft increased by leaps and bounds. I mean, orders of magnitude. And now it is acknowledged by all military and strategic thinkers, war is not winnable unless one has air superiority. Okay? And no Sanjang has ever lost a war by the force of enemy actions, whether USA or any other country, okay, who have air superiority, they never lost a war. That is what is important. So air power is the most important thing for winning the war. Okay, this is what it is. So after Second World War, there is a lot of effort and lot of investments, lot of technology development that occurred in developing fighter aircraft. The first generation fighters were 1945 to 1955, soon after World War I, World War II. They're all subsonic aircraft flying below the speed of sound. First generation jets, they are carrying guns, bombs, and rockets. The missiles had not yet come. There were no what you call radars and all, no what you call advanced sensors and all. So this is the first generation. The British Nats and the MiG-20, MiG-19, MiG-17, MiG-19, and some of the aircraft like F-18. These are all the kind of aircrafts which were there. The second generation are the which came in 55 to 60. The supersonic there. First generation radars came. First generation missiles came. The guns continue to. There was a lot of debate whether guns are required or not, but somehow the guns continue to say. In fact, the first generation, first MiG-21 aircraft, Russian design, they didn't have any guns at all. But the Air Force insisted there should be guns, so they retrofitted it. So now guns have become part of the thing. This is what happened. You have got the MiG-21 aircraft which came into the market, then F-104, F-86, lot of F-104 and all. These are the American aircraft that have come. They had a stellar role in all these things. India imported the first generation NATS they imported, second generation MiG-21 Russian. They made under license, almost 600 aircraft they have made them, okay? But they're all made under license, no technology was developed. They're all only manufacturing was done in India. Then the third generation came. And in the third generation, the European aircraft, the Mirage 2000 is an important aircraft. The F-16, the F-18, are the F-14, F-15. These are the aircraft of American origin. Very, very popular aircraft. They are the third generation aircraft that have come there. Then India didn't have any aircraft. They only imported the Mirage 2000. In the second generation, when this was going on, India tried to do an aircraft called HF-24. I will talk about it. And but they couldn't make a second generation because lack of an engine and all that. So, but it died. Afterwards, a lot of paperwork, but nothing much happened. So then the fourth generation came. So from the second generation to fourth generation, almost 30 years of what gap over there. And it is when the fourth generation came, there was a decision taken, a lot of effort gone into that we must make a fourth generation fighter aircraft, which is a supersonic, advanced radars, advanced mechanics, it had fly-by-wire system, advanced technology, and what you call low observable treatment, guided weapons, and the agility and speed became the thing. Light combat aircraft, Tejas, what I'm talking, belongs to this fourth generation, 4+ generation, what we call it. Okay. Then, of course, now the fifth generation aircraft, they're all under development. So this is the kind of a direction the fighter aircraft are going all over the world, all over the world. This is what happened. Today, the Russians are doing, the Americans are doing, the Europeans are doing, the Chinese are doing, the Indians have entered into the field with the fourth generation. We are now going ahead with the 4+5 and all that kind of a thing. Okay. So until the light combat aircraft come, all the fighters, whether short range, medium range, long range, all are imported aircraft. Either they're manufactured under license or imported over there. For example, MiG-21 is manufactured under license. MiG-23 is imported. MiG-27 is manufactured license. MiG-29 is imported. Jaguar is under license. Mirage 2000 is imported. Su-30 is made. Only the trainers were made with indigenous and all, but trainer technology levels are quite low, much lower than a fighter. So that is the scenario where when the light combat aircraft program started. I will just give you an overview of the light combat aircraft so that you understand what it is, and then we will have a discussion together. It is a 4+ generation fighter aircraft. I think comparable to the best aircraft available in this world, except the stealth fighter. It has the best technologies, best capability, and it is proving itself very good in the Air Force in India, and is also slowly being appreciated by the Air Forces in the world. And let's see what happens. So from a first generation HF-24 aircraft, which was tried to be developed in India under a German design team. Okay. They wanted to make a supersonic fighter. They couldn't do it. It was only a subsonic. But it had only first generation. It didn't have any radar. It didn't have any missiles. It was only having rockets and missiles. That is rockets and bombs and, of course, a gun. So from there, in 2000, when we flew, we moved from first generation to 4+ generation. And we a lot of innovation in composite materials in total, but composite in particular. And total flyby is an unstable aircraft to improve its agility, improve maneuverability, very advanced digital avionics. In fact, this is where the first generation code is a totally analog aircraft. This is a totally digital aircraft. All systems, including mechanical system, are computer controlled. Okay, now, so this is the jump from first generation to fourth generation. And we had to do the jumping without any experience of doing a second generation and third generation fighter. Rest of the world, everywhere, they did a first generation, they did a second generation, they did a third generation, then they shifted to fourth generation. But we didn't have that kind of a luxury or opportunity. So that had its challenges and its rewards also. So that is what had happened. So that's what I mentioned. 4th January, we did this. It's a technology demonstration. Again, demonstrating the technology. Again, operational aircraft clearance came only after this one. So it's not only the aircraft, all the technologies were mastered. And before this aircraft flew in 2001, early 2001, January, in 1998, we had a sanction from USA because in 1998, India exploded an atom bomb. So the whole project was under sanctions. Nothing was allowed to come to India. So we had to work under those conditions and still make the aircraft fly. So that was a big challenge. And before that, in 1990, when we presented a program to our government, Indian government, India was going through a difficult phase. They had no money. So we had to wait until 1993 to get the money. So we had a series of such challenges. So the project has gone through very interesting phase, but it has come out of that. So these are the basic technology. I will not go too deep, but I will give you a rough idea. See, it is all the systems, mechanical, electrical, all system, hydraulics, everything, they are dual redundant systems. All are computer controlled. This is the first aircraft of the generation which is computer controlled. The previous aircraft like Mirage 2000, F6 and all, they didn't have that kind of thing. Later on, they updated it, but this British flew with that one there. And very advanced, 100% digital aircraft. There's no analog system at all. For example, the Rafale aircraft, which is the French have developed, the fly-by-wire system is a hybrid system with the digital and analog. But we had to jump from total analog to total digital. That has its challenges, problems, and all. It also gave us some benefit. So this means a lot of technology development. We had to do that. And we had not done any work on composites, advanced components. So ab initio, we developed everything. The material development, the technology development, the testing, validation, everything was done. And our brakes were, until we developed this aircraft, they were all copper-based or iron-based. So we had to go straight to carbon-based discs, which had its own challenges and all. And this aircraft is an unstable aircraft. That means if all the fly-by-wire system flies for more than 300 milliseconds, aircraft will become uncontrollable. So that means the technology required, the reliability required was orders of magnitude higher, and that needed to be mastered. While the US had given us the engine, but when it comes to the control loss, they refused to give us. So we had to develop all these things on our own. So these are the kind of challenges which we had to face. I just quickly show some of them. Perhaps when this aircraft is almost 90% composites, and we started with zero knowledge. And when this aircraft now is among the few aircraft which are the highest percentage of composites, until the 787 came, which has got almost 60% now, that by weight. So otherwise, this was an aircraft with a very high percentage of components. I do think the next aircraft we fly will be having high composites. The fly-by-wire flight control, it is one of the most difficult technologies. Initially, USA has given us the go ahead to buy the items, but they said we can't give you the control laws which control the aircraft, which we developed on our own. But they allowed us to test them on one of their aircraft. It gave us a very interesting results. When the aircraft started flying, most of them are imported. Today, all of them are indigenous. All the technologies have been developed. The cockpit is digital. And like today, most of the cockpits are digital. And but this aircraft was the first digital aircraft which we developed and flew. What is important here is the avionics, which are flying this aircraft, navigation, everything, including utilities and all. Most of them have been indigenous, except one or two minor things. Everything else is indigenous. And the what you call the environment control system, right from day one, we developed all the components, subsystems, and made it fully operational. The Indian industry is manufacturing them all that. This is what you call a secondary power system. It has the gearbox, connects the aircraft with the engine, and it has a what you call something like an APU, which will start the engine. All these items, accumulator, reservoirs, everything have been developed, including the landing gear. It's also have been developed, which wheel brakes and brake management system was one of the challenges. It went through a lot of effort in making it perfect. But today, the technology is available with us. In fact, some of these things, it's not only the development of the equipment, but the test facilities required. They become much more complex. Sometimes I feel that took longer time and more challenge. For example, the aircraft mounted gearbox who connects the engine with the aircraft. Critical because there's no redundancy here. It has to work. And developing this, it was done by one of our sister labs called CVRD at near Chennai. It was a tough job, but they've done it. And it was a very, very important lessons for us, how it went through, how academia, industry and all collaborated. I will show you a little more on that. And I was mentioning to you about the brake systems. The complete wheels, brakes, landing gear, everything was ab initio developed. And the state-of-art technology with the carbon brakes, everything, the brake management system. It was a big challenge. And we had a tremendous collaboration between the academia, industry, and R&D. And it is one shining example of that collaboration. And big challenges, you may make equipment, you may make subsystems, how to integrate them, how to put them together, how to make the aircraft, what you call safe, and also have high performance that you are requiring. It needed enormous amount of test facilities. A few I'm showing, we had about 100 test facilities, ab initio. Nothing was available. I want to show you the Lightning test facility, the Iron Bird, fuel test rig, environment, all of them very high fidelity simulation, very high fidelity hardware, software simulation were done. And in my opinion, it is these facilities that gave the reliability, integrity that is required. Possibly this is the only fighter developed in the world which has flown for last 22 years without an accident. Whether it is Chinese or Russian or American or British or what you call European, all of them had accident. But this is the only aircraft. And I give a lot of credit to a lot of course, our controller teams and others, but also a lot of test facilities that we have created. And simulation was our backbone. We did tremendous amount of work in this area. And I'm thinking this is one area where the role of academia was extraordinarily high, right from simulating the aerodynamics, controls, human pilot dynamics, structural dynamics, landing gear dynamics, hydraulics, propulsion, flight control. Tremendous work has been done. We formed a national team, in fact, and in this team, we had industry people, R&D people, academia, all working together. And this is a concrete example of how putting all the teams together has really worked well. We used not only simulators, what we built in India. For example, we had a Dijan simulator, NAL. We had a handling quality simulator and one of our lab called ED. We also used the simulator BAE in UK. We built Iron Bird, which is a hardware software simulator at HAL, our industry partner. But we also used an in-flight simulator, Calspan in USA. In fact, the first control law was tested in that simulator. It gave us very good inputs and very good results. And it gave tremendous confidence to our pilots. In fact, one of the pilots who flew our control laws in one of the F-16 aircraft is a Pentagon pilot. He made him a very jocular statement that the F-16 flies better with the LCA control laws, which gave a lot of confidence to our people and our pilots and engineers. So So these are the kind of simulations, right from ground simulation to in-flight simulation. Tremendous amount of development work has gone in. I'm mentioning this because these simulators have played a critical role along with other test facility in bringing the what you call the control laws to the perfection that was required. Today, the controls of LCA, whoever has flown, they consider it perhaps the best control that they ever flown, and people have flown 40, 50 fighters, and that is what it is. And we have to give a lot of credit to this. So this is the Iron Bird, which is both hardware and software is there. It took very long time for us, but today it is one of the backbone pillars of our thing. Then we had to, our whole aircraft, 90% of the aircraft is made out of composites, carbon composites, and you all know carbon are not a good conductor. So we had to design conductivity into the composites. Then we have to develop the design technologies. Then we have to test them. Because the whole aircraft has to be tested with the complete system working. And that is where we had to do high voltage tests, high current tests, fuel ignitability tests, indirect. All these technologies of test technologies and all were developed at the Indian Institute of Science. And they did a marvelous job. And when the facility became operational, I was told this was the best facility available in the whole world. And the credit should go to Professor Nagbhushan and his team at Indian Institute of Science. A lot of, you have to generate a million volts, volts and million amperes for maybe a fraction of a millisecond, but that needs to be done. And this has been done. Whole aircraft has been tested with completely systems on in this facility. And this facility is now the backbone in our country, and many aircraft have been tested. And the whole wing had to be tested because lightning test, wing is completely composite. And testing that, the test facility creation was a major challenge. But I'm happy to say the Professor Nagbhushan and team helped the design team, and we did a very successful test. I wanted to show some of the gearbox. In fact, I find that developing the gearbox and getting it certified was as difficult a job as designing the gearbox itself, because it's a safety critical one. And I think the job was done extremely well by our friends in the TVRD. And there was a lot of collaboration between the industry there and IIT Madras. This is the attitude test, because you have to test in all conditions. Very beautiful test facilities have been created there. This is altitude test chamber. Whole gearbox was put in right up to 50,000 feet altitude, temperature, pressure, everything was built, tested, validated, and the gearbox has given fantastically good performance without any problem. So, in other words, what I would like to say is that when the LCA Mark I we started, our technology base level was only that of a first generation fighter, which is virtually like a metal aircraft, so everything and all analog system, mechanical, and we jumped from there to a level where today I think we have the technology base which is compatible to the best in the world. And the key technologies are designing an unstable aircraft, aerodynamic design, fly-by-wire flight control, algorithms, software, computers, everything, advanced avionics, both algorithms, software, and composite structure, very, very difficult thing, but we have done it well. And computer-controlled systems, electrical, mechanical, and all. And testing this aircraft itself was a challenge. And certifying this aircraft was a challenge. And creating facilities for design qualification about technology itself was a challenge. So all these were done in a single project. We didn't have any one of them before we started this program. So everything had to be done ab initio. And but the way it was done, I would like to spend some time and explain to you what we have done that. While we were doing that, the Indian Navy said, why don't you design a fighter for us? So we developed a light combat Navy, naval fighter. This also, it's not a simple game. We have to take off and land from a carrier. A 2 kilometer runway is there for Air Force, and this is 200 meters, although 1/10. And the aerodynamics is different, flight controls are different, everything would be different, structure is different, but all that has been done. You can see here, it has additional controls called leading edge vortex controllers. Possibly we are the first in the world to develop this for a naval fighter. It has flown successfully. A lot of, and we have built a test facility to do that. You can see all the technologies, what has flaps, leading edge flaps and all. We built a shore-based test facility where complete aircraft testing could be done. And then once it is proven, you come to the carrier. Maybe this is the test facility which is now being used for Rafale, our MiG-29, all the aircraft which are there, because an excellent facility, world-class facility, which anyone could be proud of. As we are going ahead, I'll say Mach 1, what you say, Mach 1A with a better engine, better what you call radar, better weapons, and all that is going on. It's part of the job. We also have got, I'll say, Mach 2. In fact, today the Mach 2 also, the project has been cleared. Money has been come. Now development work is in progress. It is almost, you can say, almost 70 to 80% higher payload. It has a GE 414 engine. You see the complete program. One area where we have not yet got a fully certified engine is the engine for the light combat aircraft. Okay, it's still the indigenous engine, not yet ready, reliable enough with the kind of performance we want, which can go on to a single engine fighter. Okay, so we continue to use an imported GE engine, and of course, a lot of work is going on. I hope we'll succeed. It is work in progress. We have a 5th generation fighter. The design has been completed. It is a stealth fighter, much what we call a next generation kind of technologies, and it can fly. It can be in a non-flight mode, as I'm showing here, or it can be a flight mode. There are no external weapons and all weapons will be internal. So it advanced medium-range combat aircraft. This is also, the design has been completed, but awaiting the clearance, because they were expensive. A similar twin-engine fighter for Navy also in the development. So this is the kind of very low RCS, okay? That is the kind of thing. Twin engine, much bigger, and it has to be a net-centric warfare. So all these aircrafts are now what you call enabled with the technologies that become integral with the net. Okay, it has to be integrated with the satellites, communication satellites, and with the unmanned air vehicles, manned aircraft, combat unmanned vehicles, surface to air, air to air, and sea to air. All these weapons have to be put together. All these aircraft, what I'm talking, are compatible with the net-centric warfare, including the LCA. This is the 6th generation unmanned combat aircraft. 6th gen combat, fully stealthy, and this is the new technology work that is going on now. A lot of effort is going on, but this is on the anvil. Okay, I won't be able to talk much about it, but a lot of things are going on. And it's a flying arrow wing configuration. This aircraft will have our indigenous dry engine. Okay, this will have. It will have an internal bay. It uses a lot of technologies we have developed from LCA, light combat aircraft, but also uses the technology developed for a lot of unmanned air vehicle programs, which our sister lab AD has developed, and a lot of mission sensors have been re-engineered and going on. So this aircraft, I think, with the indigenous cut, including the engine, will be indigenous, and also looking at the manufacturing be done in a big way, so that this aircraft cost effectiveness is an important thing. So you can say, starting our base was 1st generation, we build a 4th generation, it became a 4th plus generation, then a 5th generation, then a 6th generation. That is what is happening. And this is what it summarizes. With LCA Mach 1, Mach 1A, which is now in production, Mach 2 is in advanced stage of prototype development, and Mach 1, the 5th generation fighter, Mach 1 and Mach 2. Today, Indian Air Force is thinking of 100% indigenous fighters. From 100% dependency, I sold that to 100% independency. And not only that, with the technology level, which is comparable to the best in the world. So the LCA program is enabling the country, enabling Indian Air Force, subsequent Indian Navy, to jumpstart from total dependence to total independence. And that is what is the outcome of light combat aircraft program. Now I'll tell you what we have done, what are the things. I will spend a few minutes, then we will have a discussion quickly on that one. This would be the largest and most complex technical program India has ever taken up. Okay, that is what we have done. India didn't have any capability, I have mentioned. No single organization had a capability. So a new organization called Aeronautical Development was created. It is a structure within government, but autonomous with the required powers. It is registered as a society with the defense minister as the president. But society has been made more autonomous so that we can take decision at the project level rather than going to government for everything. And I want you to see this, why this is important was the normal functioning what we do in a big organization, a government is goal setting, you follow a clear-cut plan, reduce your risk, the process is standardized, centralized decision making, and authority, whoever is working, war-reaching authority. But that way, we felt that is impossible. I took over in 1986, end of 85. I felt that incremental thinking, what is common in industry and government, will never allow us to develop from a first generation to fourth generation with almost nil infrastructure in aviation in India. Okay, some manufacturing at HL was going on, but technology level was hardly anything. So we had to have ambitious goals. Okay, from zero indigenous to massive indigenous content, very ambitious goal. We had to have a vision because when I joined the organization, people said 99% chances of failure. Okay, but so you need to have a vision to do. We had to learn where do we go ahead with the project. Extraordinary amount of learning, and it is not like a what you call impersonal. Personalize the whole thing. People who are working anywhere in the whole country, outside the country, there was a personalization of the effort. Okay, and empower the decision making. And instead of expanding authority, we expanded the influence. That is the key point. I thought the important change is from incremental thinking to exponential thinking. That is exactly what we have done. I thought this is important for my presentation. So what did we do? We developed the core technology. We developed the enabling technology. Tremendous effort gone in modeling and simulation, and tremendous effort in integration, and a lot of effort in developing system safety. Not only component, subset system safety. I think that is what there. So we have a flexible management. It is a virtual corporation. There is no other thing. All centers of network. Okay, we had 300 industries, so some more than 2 dozen academia, about 40, 50 labs, and everybody worked. So there is a strong linkage between industry, lab, and academia, I think. And wherever we found no lab, even with support from others, cannot achieve, we formed national teams. For example, controller development, we formed a national team. To make a complex composite wing, we formed a national team. So like that, we did that. A very strong corporate quality system, because the level of quality that you require, the level of integrity you require. So this is what has been achieved at aeronautical development. So organizational innovation, along with, and my understanding, if you don't have the organizational innovation, not possible to do that technology. And that is what we have seen happening. As I mentioned, the whole country participated, hundreds of work centers, from a small and medium scale industries to big industries, R&D laboratories, the CSR lab, atomic energy laboratory, space laboratories, DRDO, and most of the industries, small names who have not had, and all the major academic institutions, all the IITs and others, and including organizations like PhD College of Technology, they all participated in a very big way, and its participation is not peripheral. It is central to the program. And we developed 3 types of people: specialists, analysis, lot of work has been done, academia and R&D there. And but also you need people who are architects, system integrators, configurators. That is what at ADA we tried to build this capability, both analysis and system integration. A lot of capability we developed at industry also, and a group which is looking at scheduling, budget, business, and all. So if you are building an aeroplane, it's not only airplane, anything. You need all the 3 kind of people, and this is what we built the capability. Okay, and all 3 learned how make people work together. So system thinking, you are talking about design thinking, and also that is what we built the capability, and that is the capability which is taking us from LCA to, let's say, Mark II, to MCA, 6th fighter, and all that kind of thing. And the network that has been created and the personalization that has been done, which is helping us to move forward. So we had this kind of a knowledge generation, as I mentioned, the design team, the labs and academia, work has been done. The knowledge validation, that, and then knowledge intensification, system labs and HAL, system labs, so there, knowledge validation, certification, and knowledge transfer gone to the, what you call, the production agencies. So all the 4 elements have been tried, tested, validated, and now the work is going on. There always challenges, but work is going on. Okay, what has been done? My understanding is mission, LCA was not just a project, it was a mission. Lots of ideas, a lot of thinking, a lot of things have done. And that enabled us to develop skills and enormous amount of facilities. And that also enormous amount of technologies. And then we developed equipment, systems, substrate, and systems thinking. Above all, what you call as a culture of working together. And that is what we have done. The support system, what we created was a support system for innovation and knowledge generation. And that is what I believe is very important. It is the exponential thinking that we brought in, where people were willing to take a risk, willing to try an technology, willing to fail, but fail fast so that you are able to overcome, understand the failures, build a good system. All that has been done in a single program. Okay, and that is what is important. And I think the legacy of this program, of this aircraft program, is the support system for knowledge generation we have created, the technologies we have created, and the networking we have created. See, in India, that kind of network between academia, R&D, and what you call industry was very little, hardly anything. And this program has proved beyond doubt that such a network could be created, could be sustained over 2 decades, and could deliver goods, and that network is continuing to support the country into moving forward. So I thought that is what is important, and that is what we have done that. And let me now end it. Finally, it is one of the quotes I thought I will like to. It is love for what you do. It is the passion. It is what drives you to go against any kind of roadblock or difficulty. You don't care about incentives of the company and the tools they give you and the KPIs to measure you, because you are driven by the passion, do the right thing and change the world. I think this is a very nice point. I thought I will end my talk with this and we'll discuss further. So thank you very much. Now I'll stop sharing, okay? And if it's okay for you, then I will stop sharing and then we'll discuss.
Thank you very much, Dr. Kota, for a really excellent talk. And I think the important point you made towards the end is the organizational point of how to build such a network and really bring all the capabilities together beyond one organization, which is something, of course, living in the US, I see all the time. And to see this in India is really, really coming together and doing something for India is really remarkable. And really, not only congratulations to you, but to your whole team in bringing India to a new way of thinking about building aircrafts. And I hope the same ideas will percolate to other industries. Sometimes I'm not that hopeful, but I hope this would be an exemplar for the rest of Indian industry as well, to move forward in the Indian technological superiority as we may gain over time. We'll open it up for questions, and please head and talk, Shyam. Go ahead.
It's a very informative and interesting talk. So thank you so much for this talk. I want to follow up on your last point and what Sab said. When we look at development of aeronautical industry in US and Western Europe, it was a collaboration between government and profit-making corporations. In Russia and China, Soviet Union previously, was largely has been largely in the government sector, as I understand it, where a profit motive is weaker or absent. How do you see the structure, organizational structure, and the role of economics and profit motive in the structure of the aeronautical industry and technology development and manufacturing in the future in India? Thank you.
To mention to you, before this aircraft program was taken up in India, there was no ecosystem. There was only one industry called Hindustan Aeronautics Limited. They designed some trainer aircraft and all. Otherwise, they were manufacturing under license. The ecosystem that is required with large number of tier 1, tier 2, tier 3 partners with a strong academic background, that was non-existent. And that had to be created ab initio. And I think one of the biggest, outcome of this program, it's not a project, is not so much the aircraft alone, but the ecosystem creation. And today that ecosystem, which is sustained itself for 2 decades, they know how to work together, how to understand each other. Earlier, each organization will think what are the weaknesses of other fellow, but now they think what are the strengths of the other fellow. Okay, how to supplement and complement each other. So I do believe that not only though the whole work is a fighter aircraft, but the ecosystem will sustain a transport aircraft. We are now looking at development of a 100-seater passenger aircraft, okay, because that is where the big demand is there in a developing country, in a country like India. We are the largest demand in India. So that is what we are working on. But this ecosystem will sustain that. This is what is the important point. We also had a problem because we had the US sanctions, the Europe was not supporting. But what I have found is sometimes a sanction is a blessing in disguise, because people don't give you, you develop yourself. Okay, and today I don't think there is any problem, because people know if we put any restrictions, people will do. I used to jokingly tell the then US ambassador, every 10 years you put as a sanction so that our technology will improve. So of course we now are good friends, so things are going on well. So, but that's what it is. I think the biggest challenge is creating an ecosystem and people willing to take risks. I think the new structure we created, a new organization, it is a new, totally new. There was nobody in that organization. Everything was done. And people who joined are people who know they have to take extraordinary amount of risk. Okay, so that is what has happened. Sabu, you want to add anything, or you want me to ask anything further?
No. I think you have covered most of the things. I think especially the organizational stuff and the building the ecosystem, which is something I think a larger lesson has to be learned from this for the entire country. Now I will go to the next person who has raised his hand, Vijay Raman. Please go ahead and talk, ask your question.
Thank you, Professor. Dr. Kota, I don't think you'll remember me. You gave us a lecture at the IISc, which we organized on your aircraft together with some just before COVID broke.
Because I remember now. Yeah. Good.
So
nice.
I just wanted to ask you a question. You explained to us in very clear terms that you moved from the first generation to the fourth in aircraft design and subsystems and so on and so forth. And it's been a wonderful way in which you have progressed by thinking of the organizational requirements and emphasizing the need to work together in production, in industry, with academics, and of course with the impetus of sanctions of some sort or the other, where we are denied technology in the country. Now, you have given us two very interesting views in your dissertation today, which is that you mentioned that for unmanned aircraft, you plan to do that as a mission which is complete, including engines. But of course, that is at a much lower power requirement than a lead fighter aircraft. So, isn't it necessary that we should now be, I mean, maybe we already are in it and people are being secretive, but we should be in the same mission mode that you mentioned for everything aeronautical, also for the engine, because that's the elephant in the room, according to me, that after 70 years, we still have to put in for our lead fighters, fighting aircraft, we have to get in imported engines. And we do that not because we think they're superior, but because it is so difficult to get that job done by ourselves that we have to take practical decisions from time to time. So I know we have other problems too, which cause interference in the way we progress towards the goal. But I wanted to hear your views on how we can set up in the engine sphere the same kind of ecosystem you now have achieved in everything to do with an aircraft structure and its subsystems.
What I'm happy to mention to you that as far as the engine for the 6th generation unmanned combat aircraft is concerned, it is taken good shape. There's a good collaboration between the industry, R&D, and academia, and the test results have shown quite well. And as you rightly said, this being a stealth aircraft, it will not have any reheat and all that one. The thrust levels required are low. But from what I understand, my friends from Engine Design Bureau, that they have done good progress now. I have zero doubt in my mind that the 6th generation unmanned combat aircraft will have an indigenous engine. I have zero doubt in my mind. Okay, my main thing is for the manned fighters. Of course, recently India and USA have agreed that the G engine will be manufactured in India. But that's good. But because the supply chain problems, so you don't want to get into them. But what is important here also is that this creates a good manufacturing ecosystem in the country, and the technology base we are creating, but some more work has to be done, so that eventually that engine also will be an engine which will meet the 5th generation fighter. That's what we call LCA Mark II, not AMCA Mark II. That is what it is. Okay, but 6th generation unmanned aircraft, that engine, it has taken good shape. But the engine people also have learned, they have studied how we have gone about with the aircraft. And I do believe the lessons learned will be utilized by them. Thank you for the question. But I want to mention to Vijay Raman, the involvement of academia, among them Indian Institute of Science, has been extraordinary. And you know, Professor Narasimha was very deeply involved in it. He, as a professor and subsequently a director and AL, he was deeply involved in that. And there was recently an article which has come about how he had thought through. So this is one thing which is shown to Indian industry, that academia's contribution can be not just marginal, can be crucial. That's what it has proved. Yeah.
Sudhir, you wanted to ask?
Yeah, so my question is more related to the same academia. How do you see this kind of experience translating back into the academic programs? Have you seen that happening from Tejas, or what do you think can be done to bring this case study at all the granular level back into the academic program?
Good. I'm very happy you asked this question. I want to tell you the way our academia has involved itself in our program. One, of course, a lot of projects they have done. For example, Indian Institute of Science alone have taken about 130 projects from one program. Okay, and right from building the test facilities, building, modeling, simulation, design, everything. A lot of. The second thing is, some of the faculty joined the LCA team on sabbatical. In fact, they become part of the team. They came on 1 year sabbatical. They came on, some of course even joined as, they left their job from abroad in India and all, they joined as a full-fledged. Some came for 1 year sabbatical, some came for 3 months sabbatical. And whoever came, they developed a lot of things. So I will give you one example, you will understand. This normally we talk about aero servo. The structure and aerodynamics they interact. But here we have controls. So aero servo elasticity, aerodynamic, structure and control, all the three interact. And this technology, this software, these algorithms, we didn't have. So finally, Professor Suryanarayana from IIT Bombay, he came to ADA, he spent 1 year, he formed a joint team of HAL, NL, ADA, AD and all, put all the discipline together. By the time he left, the software required for analysis of the aircraft, for design of the aircraft was ready. In fact, even for money or for anything, nobody in the world were willing to give us anything. But here is an example where a person who is a well-known man in the field, but he came to us. I want to give this as another example. One is taking projects. Second is you jump into the program, join them and work with them, because there are certain things which may be impossible to do unless you are in this multidisciplinary environment. And that is the second thing. Third thing, what happened, he and some of the other faculty from IIT Bombay, IIT Madras, Kharagpur and all their PhD problems were problems that they took from a program. In fact, 6 PhDs that came out of Professor Suryanarayana are all these subjects, variants. And that is pushed the, what you call, knowledge, understanding science and technology to next level. In fact, that group became the best group in the world. So there are 3 ways. One is, of course, you participate as reviewers and all, which happens. ISRO it happens, and DRDO it happens with us. We never do a program unless there is a strong academic partners who look at what we are doing. In fact, our control laws in the review, what validation was done by an independent group headed by professor from Jadavpur University. It's not IIT, it is Jadavpur University. Okay, so it's not that as if it is only IIT, IISc Chakkar. No, Jadavpur University, Professor Gosal was the head of the controller team. It is he who would run. It is who gave the clearance. Okay, and we have built a lot of facilities. We include autoclaves. It is the team there who have validated the whole thing. So you could see that in all the 4 or 5 roles, the academia must work. You should not be limited to only projects. Projects are important, but also jump in, become partner, because it's a complex one. You have to get into the skin of the problem. You have to get inside. Then only you will understand the good and bad of a program. Okay, and that is what has happened. I thought this, in all the roles, I feel academia must participate. Say, a sabbatical should not be always going abroad. Sabbatical could be for a project in an industry in India. So that is what would be my takeaway from this program.
Any further questions from anybody in the audience? Please raise your hand or unmute yourself and go ahead and speak. If there is nobody else who's going to ask any questions, I have a question for you, Dr. Kota. How do we take this and educate our industrial class, let me put it that way, that without such an ecosystem, India can never do Make in India in a meaningful way. And they have to cooperate and build such ecosystems for almost every product, whether it is cars or infrastructure or anything of that nature. What would you give their advice?
Software,
yeah,
and some advanced programs, some technology development programs. Even at a TRL level 1, 2, 3, 4, we have to invest. Somehow the industry's investment has not been high. Okay, but it is a military program, so the government could put money. But if it is a civil program, industry has to invest. But one thing, the Hindustan Aeronautics Limited, who was very skeptical about the thing, today they are changed. They know that it is the ecosystem which is supporting them. Without this ecosystem, they could not do. I do believe that other major programs which are there, they will also learn and they will also understand from this. And let's hope. I'm sure if you are taking technology from somebody and to do it, then it's different. If you have to develop, if you have to be competitive in the world, you have to develop the things. Okay, there is no shortcut here. And I do think that industry will understand. I'm looking forward to Indian industry taking it up in a big way. Okay, let's hope it happens. But here is a concrete example of everything going in the, what you call, against you, but still you have come out successfully. That is the point.
So with that, if there are no questions, I'm going to mention that next Wednesday, Professor Yoram Reich, whom Dr. Kota has met from Tel Aviv University, will be talking about designing design education, his own personal experience. And after that, there are 2 other lectures. We will have a hiatus till August 9th. The August 9th lecture is not yet finalized. And Sudhir, do you want to talk about, say something about the next 2 lectures? Because you know the 2 people who will be talking in those lectures.
Yeah, so on 23rd August, we will be having a talk by Professor Ramesh Babu from IIT Madras. He will be talking about the Manufacturing Center of Excellence, how they went about developing the Center of Excellence to support manufacturing machine tool industry. That is on 23rd August. And then on 6th September, we will have Dr. Bhuvaneshwar talk about the development of medical devices. He was involved in the Chitra Tirunal heart valve development. So he will speak about that's again like almost like a 15-year journey in developing that product.
Very good. Also, is a time-consuming affair.
Yeah. So these 2 talks are lined up for 23rd and 6th September.
Thank you. Thank you,
And
sir.
also, there is another
Thank you,
talk
Sudhir.
which will be organized on August 9th, which is open now. We will be having somebody talk there. So we will have a hiatus from after next week, which is after the next Wednesday lecture. We'll have a break till August 9th, given people are traveling and other things. So we hope all of you can join further in the future lectures, and we hope this provokes new ideas, new thoughts, and new way of thinking in India. And that way, Dr. Kota, you have put really a flag out there, which people have to climb the mountain to get. And really, thank you very much for a lovely talk. Thank you.
Thank you. Thank you for that.
Yeah.
I'm leaving now.
Yeah, thanks. Bye.
By the way, the Dr. Kota's talk and other talks are on the are going to be on the website or are on the website of CRAE, and you're welcome to see them in the recording form.
Thanks, Shyam. I forgot about that. Thank you, everybody.
And if anybody in the audience or others who have ideas on, please be in touch with us. And we would like to build this community of CRAE. Is the idea of building a community which of people who are interested in reimagining engineering innovation. Thank you.
Thank you, Shyam.